Alrighty, I might get started. I don't want to run too much over time. Thank you everyone again for attending the first Green Chemistry Connections event. Our third speaker for this evening is Professor Qin Li. So Professor Qin Li is a Professor of Environmental Engineering at Griffith University. She had obtained her PhD in Chemical Engineering from the University of Queensland in 2002. As a chemical engineer and nanotech scientist, Professor Qin conducts her research on functional materials and applied nanotechnology to provide solutions for environmental monitoring, water purification, waste reformation, and renewable energy. So Professor Qin Li is also the co-founding chair of the Green and Sustainable Chemistry National Interest Group at RACI and advocates for innovating sustainability. So today, Qin will be talking about the importance of waste-derived carbon quantum dots as one of the promising materials in circular economy. So I will let Professor Qin take over.
Thank you, Tessa. I'm just trying to bring out the right screen. Just bear with me for a moment.
All good.
Okay. I think you are seeing my messy, desktop screen. All right. So I'm going to actually. Sorry. My apologies. So I'm going to talk about the quantum materials in circular economy, and then you will find my content is probably at a different development stage in comparison to what Colin and Peter has described.
Qin, do you want to just share your screen? Put it on PowerPoint presentation mode, just because we can see the
entire, yes.
Yeah.
Somehow okay.
So you can go the bottom. Yeah, there we go.
Okay. Right. Okay, and I also would like to correct one piece of facts. The Green and Sustainable Chemistry and Engineering is now a division approved by the board of ICI. So it's grown from a national group to division. And I still can't, okay. All right. So now we have heard about the concept of circular economy, and I do quite some research on energy, environmental protection, environmental sensing. And so my thoughts immediately just goes to some energy harvesting, this kind of application. And we know about the CO2 issues, our planet boundary issues. And some of the solutions we come up with, for example, we use solar cells to capture to harness the solar energy, and then we wanted to use the electrolyzers to produce hydrogen, and therefore we can remove the fossil fuel usage. But on the same kind of page, we also have the alternative, that is using the biomass to absorb the CO2 and then to solve the problem and then can provide energy source. And I think there is a natural world, and then there is our man-made, that artificial world, and we are sometimes we are competing, sometimes we actually should really find the right balance. And on both of the fronts, whether it's biomass or whether it's man-made objects, they all have its end of life or end of one useful life. And we heard about how to extract things, how to repurpose, how to redesign and resynthesize them into, I think what we have heard particularly is in the functional materials, composites, polymers, and sometimes we also heard some mention about construction materials. And we did hear about high value extractions. But there is also another pathway, is to make them into quantum materials. And so now the question is, what are quantum materials and why do we need quantum materials? And to chemists, it's not necessarily so obvious, the quantum material, what they are. So this is a diagram of Moore's law, and it's about the transistors size and how much transistors we can fit on a very small chip. And so we have this double up, every year, and we have come to the stage we actually can manufacture 2 nanometer kind of feature size the transistors. So it's magnificent achievement, but it seems that we have come to the limit. But the trend, we never go to somewhere and just fall off the cliff so far. And so how are we going forward? And we are now, the physicists probably are leading the game at this stage, but I think there will be a change that chemists will really take over, because we need to make it, to implement the concepts, to the theory, to make it work. And that requires our efforts. And so quantum materials are these materials, they do not follow the classical, the physics laws, and they use excitones, they use magnons, and they use all the exotic properties, or they exhibit exotic properties. So here are some images I have taken to show you these photonic chips for fault tolerance quantum computing. And so using the light as the information carrier instead of using electrons. And this figure also shows the light-based. You can see it's almost like a neuromorphic kind of things. Some of the calculations can already be embedded in the photon interactions. And the right side of this image is probably easier to understand, because it's a 2 photon. That this is a graphene nanoribbons, and they can emit in the near infrared. And these 2 photons adding together form a logic gate, and then this plus will trigger a signal propagation. So these are some examples about the quantum materials and how they are used in quantum computing. But this is still a very simplistic kind of picture about that concept. And we can even go more simpler and make quantum chemistry, quantum mechanics talking to us. So quantum dots are already a reality in some applications. So for example, this the LG quantum dots based display, and the very defined high resolution, these colors is due to these quantum dots. So you get very intense bright colors and also with this high resolution, because the quantum dots are a few nanometer in size. And also with solar cells, we know the researchers in solar cells, they always compete for the efficiency. And this quantum dot-based solar cells has been regarded as the next big thing in photovoltaics, because this can use all the energy that is wasted in the conventional solar cells, to use that energy for the electron, the productive electron production. But here, probably need to pay attention to this 2013 paper, and so quantum dot layer, and they were talking about lead sulfide, lead selenide, cadmium selenide, cadmium sulfide, all these heavy metal containing quantum dots. But photovoltaics application, this is established. And we are using also the excitones for photocatalysis, for environmental remediation. And sometimes we use that for chemical synthesis. We also can put these quantum dots into the plants to make bioionics. We also do the bioimaging. And some diagnostic plus therapy type of studies are also hoping that quantum dots can bring some new vehicles. Well, I already have pointed out these heavy metal containing quantum dots, and for the people who are sitting in this on this Zoom screen, and immediately, it's not going to go very far. And so we do need to look into the sustainability and the green chemistry. So if we look into the green chemistry 12 principles, we need to see how many of these principles we have actually applied in this quantum materials design and synthesis. And these 12 principles can be summarized into 4 categories. One is the sourcing of the feedstock components, and second is processing methods, whether it's efficiency, whether it's producing derivatives. And the third is applications, its performance and in energy and its lifetime. And the fourth is the end of life, whether they can be recycled easily, whether they can be reused. So if we use these 12 principles to guide our assessment on the suitability of these quantum materials, we can form a better picture on whether it's going to become a benign and useful material for the society. So my team, favor these carbon-based quantum materials. So what's on the what's on the screen? They are all can be quantum materials, and of course graphene. Probably in this context, we talk about defective graphene, and which does have some quantum effect. And carbon nanotubes, fullerene, and carbon dots, or graphene quantum dots, they all have very exotic properties. And we have done some analysis based on these 12 principles to just categorize, to assess how good these carbon-based quantum materials are. And we have given half a star, for some of the demonstrations, and more demonstrations, 1 star. And so here you can see the evaluation. And so carbon dots, carbon nanotubes, and graphene materials, and they're put in comparison. And carbon dots seem to be winning in this green chemistry principle. But what is falling short are the design for energy efficiency, not really looked into heavily yet, and reduce derivatives because of the thermal process used by most of the researchers. It's not taken care of properly yet. And design for degradation is not yet a top agenda. So there are definitely quite a few things to do, and also real-time analysis for pollution. So what are the carbon quantum dots? The carbon quantum dots are these tiny little particles, actually usually smaller than 10 nanometer. The scale bar here is 10 nanometer. As you can see from this size distribution, and for this sample, the mean size is about 3.5 nanometer. And these, on the screen, these particles are derived from seaweed. And what is really extraordinary is about their optical properties. So they have these fluorescence, and most of them show excitation-dependent emission. Some of them show independent emission. And they are photostable, more stable than the pigment molecules. And then because of the carbon chemistry, they have very versatile surface chemistry. In comparison to the heavy metal-based quantum dots, and also some metal oxide-based quantum dots, and just by looking at the element, they should be more eco-friendly. But I think toxicity is a different issue, and we should assess them case by case. And even in these carbon dots, this family, we have a few subsets. So some are amorphous, some are like a graphene quantum dots, a few layers, some are carbon quantum dots with a few layers, and some are less carbonized, and we call them polymer carbon dots. The example I wanted to show you is a study, done by the student Amandeep Singh. So he used the hair to make the carbon dots, and so we applied the oven heating and microwave heating, these two methods, to make the carbon dots, and they worked really well, and they come out as nitrogen-doped carbon dots. And so we made the OLED, so we used the carbon dots as the emitting layer in the OLED structure, published in Advanced Materials. But what I'm more proud of actually is this study that we use these carbon dots to sense chloroform. Chloroform is one of the trihalomethane molecules in the water, as the result of disinfection, oxidation process, chlorination process. And WHO and all the water authorities have very clear, upper limit for how much disinfection byproducts should be allowed in the drinking water. And but the monitoring is actually not so easy, because you have to do the chromatography analysis. So the sampling frequency probably in most of the places is not that high. So we were trying to find a good sensor for chloroform, and for all of them, but chloroform is the major component, so that's a good starting point. And these hair-derived carbon dots turn out to be selectively responsive to chloroform, and that at a concentration with a detection limit below 3 ppb, parts per billion. So that fits with the drinking water standard, because in Australia, 250 ppb for total trihalomethanes, and in the US, it's 80 ppb for chloroform alone. And this response is quite selective, as you can see from these bars, and the response direction is actually to enhance the fluorescence. So what's happening here? So we did this DFT study and looking at the excited state. And so we looked into the lower unoccupied molecular orbital and the electronic distribution. And before doing that, we did affinity study just to look at, the pyridinic N oxide, that moiety on these hair-derived carbon dots, how strong it binds towards these different molecules. And strikingly, they are actually very similar. So it's not the affinity, binding affinity that triggered that selectivity. It's something else. So this DFT modeling for the excited state actually shows the chloroform and bromoform. They are very similar, but chloroform, this interaction does not draw the electrons from that lowest unoccupied molecular orbital, but bromoform does. So that's the reason this probe is selectively responding to the chloroform. And so that's, I think it's an example about the sensing at excited state. It's the electronic configuration, and it's not because of the binding affinity that we usually utilize. And then some people could say, well, these kind of carbon-based quantum materials probably just don't have as good performance as, for example, cadmium selenide, because the quantum yield is lacking, and simply they are small atoms and not very rich in electrons. But I think the take is we can enhance that. Tessa, how many minutes more do I have?
You've just reached 20 minutes, so wrapping up.
I'm wrapping up.
Please. Thank you.
So what we can do for this kind of quantum materials is we can use this matter surface to enhance their performance. So here is the example about using the photonic crystal structure to enhance the fluorescence. So what we have traveled through is to use photonic beads. So this blue color on this screen is purely from this polystyrene photonic beads. There's no dye, there's nothing else, and it's showing a very angle independent, this color. And then when we use that as a carrier platform for the carbon dots, and we get beautiful, very, very bright, the blue for the carbon dots, and also the color purity is enhanced. So this is to show we can enhance their performance by the topological structures. And this the mechanism of this resonance in resonance. Yes. And we also utilize this for we took the inspiration of this pyridinic N oxide terminated carbon dots for chloroform sensing and combine that with the colloidal photonic crystal, and we made a simple sensor. And so there's a lot of chemistry synthesis involved in that, making hollow mesoporous silica spheres and pack them into photonic crystals and then load carbon dots in, and lots of fundamental science into that. So it's very much in the R stage, but we are showing we can drive that performance and drive the application. So just two final slides showing the seaweed utilization, and we put seaweed into oleamine, this kind of solvent, a typical solvent for quantum dot synthesis. We made very high quality carbon dots. So this is the emission band, and it goes from 400 to almost 700 nanometer, and with distinctive bands. So very rich emission profile. And if you look at the TM images, you can see, well, these are really crystalline structures. And we also found, because of the ligands and the surface chemistry, and this probe is selectively responsive to zinc ions. And this is about room temperature synthesis with Professor Colin Reston, about how to make the synthesis approach greener and to be more energy efficient. And we can make full color carbon quantum dots. And then we also can make heterostructures to combine the carbon quantum dots with zinc selenide quantum wells. And then we can drive the reactions, chemical reactions. We can drive the synthesis of from methanol to the ethylene glycol and producing hydrogen. So these are the studies. We are very much at the this stage, but we are looking at industry partners, research partners to push the boundary and to drive that into applications, so we can provide a new avenue to upcycle the waste and to make them into high quality functional materials. Thank you.